Alrighty, today we'll be discussing two qubit systems, tensors and Bell states. So for this tensor product here, we define it as the tensor product between a matrix A and a matrix B. Now this matrix A is then distributed into its components as seen here, and the B is then expanded into each of its elements. As we can see, for example, with the poly X and poly Y, when we expand it into each of the respective elements, it multiplies the element number. So here it's 4 and here it's also 4. So I'm taking poly X tensor producted with poly Y, and when I do that, I basically multiply each matrix times the element, and that expands then for each element here. So for 0, that multiplies to each of the element and sort of expands, and so we get each element down here being 0. Similarly with 1, that also expands out here, and all of those elements are preserved. So that's how it's done in matrices, sort of constraining ourselves a bit more. If we look at the example of state vectors, which are defined in terms of the complex dimension, we could also say that a alpha 2 here and beta 2 here are elements of the complex dimension as well. When we take their cross product, rather their tensor product, we get this distributing. So when we take this distributes to here and here, and sort of expands. Now we can see this is reminiscent in some aspects to a dot product, but instead of each respective element here and here sort of being combined and multiplied then added, they're sort of preserved as this sort of expanded matrix or vector. Okay, so now if we want to talk about this sort of example here, where we're analyzing the 0 vector state and the 1 vector state, we can say, okay, basically the tensor product here is just that same process of taking this and expanding it here, and then distributing the multiplication. So with this, a more compact way of writing it is like this. So you'll often see when a bra or I guess if you could say, if you have a bra, for example, 0 and the bra 1, you could also write this definitionally as 0, 1, but most commonly we're going to be looking at the ket. So the ket tensor producted together gives us this. Okay. We can also do a bra tensor producted with a ket. So a ket being here and the bra being here, we get a sort of matrix expansion rather than a vector expansion, as we see here. So this sort of becomes this unique vector state, if you will, although that's not precisely true, because that's only the case for when they are the same. So for example, this tensor producted with this, we would call that as being the vector state. Okay, so now expanding this into higher dimensions, we can see that if we have 4 elements here rather than 2 elements here, sort of doubling the number of components such that they are all of so alpha 1, 2, beta 1, 2, gamma 1, 2, and delta 1, 2. These collectively are all elements of C. So they are all elements of the complex dimension, or of one real and one imaginary dimension. And we can say that that would mean, because there are 4 of these, that we say this is of C4, or 4 complex dimensions. So when looking at one qubit, we can sort of visualize that on the block sphere, as we've discussed before. The constraint of this being for a single qubit, it's basically described via its linear properties of 2 orthonormal bases. So in this example that I've written, it's 0 and 1, where it's constrained to the surface. That's basically what this is saying here, is saying, okay, it's going to be of unit length, so only things of unit length exist. And we could talk about this sort of what's inside called a mixed state, and what's on the surface is a pure state. The pure state is, well, purely defined with these quantum processes, this sort of not necessarily entanglement, but entanglement would be described explicitly on the surface. And so within it you can get mixed state, and in some sense it's useful for manipulation, but that's beyond the scope of this video. For a 2-qubit system, we often define that as this capital psi to differentiate it from a single qubit system. And most generally, it would be defined as this, where you have your orthonormal bases for your 2-qubit system. That is where your tensor product together in every possible combination of said orthonormal bases. So in this case, it's 0, 0, 0, 1, 1, 0, 1, 1. Those are all the possible combinations in binary, right? So you then have a unique value for each of those, and a squared plus b squared plus c squared plus d squared are all equal to 1. And in fact, they themselves can be complex, so we're just going to put that mod there in order to constrain that. Okay, so now to then describe this specific example of the 0-0 Bell state would be to say, okay, we're then we're still constraining this to being 1, right? So basically we're saying A is 1/2 or 1 over the square root of 2. And so we could say A is equal to 1 over square root of 2, and B is, or rather D is also equal to 1 over square root of 2, and that would give us our singlet Bell state as we have defined down here. So expanding that, we get to this form, and we notice that this can actually not be represented by a tensor product. You can try to do this, but you'll never be able to come up with them that can be explicitly defined in this form. And so you sort of have to split it up into these components as we've done here, and that is really the fundamentals of entanglement, is that sort of aspect. Sort of looking at this sort of application, we can see we have 2 qubits down here. They're unentangled, and we're going to send it through this circuit. So when my zero state hits this X, what it's going to do is we're actually going to have basically x and then almost times this, really. And that is going to be tensor product with this other state because that is describing the whole system, if you will. So when you're seeing this tensor product, it's really just describing, okay, these two together, what is the collective state of the system. It doesn't necessarily represent entanglement, because remember, entanglement means it can't be represented in this form. But right here, we'll see in just a moment that based on orthonormal, well, I should specify explicitly where A and B are orthonormal base. Well, no, I mean, I guess it doesn't even matter. They don't even have to be orthonormal bases, but it's just generally defined. Okay. So what does this mean then? So when we expand that, our x, our 0 gets expanded into x. And so we define this as 0, 1, 1, 0. And then this, just giving myself a bit more space here. Alrighty. Then we say, okay, this is 1, 0. And this is also 1, 0. And what happens here is that the top basically gets distributed here. That becomes 0. The bottom becomes 1. So now we have the tensor product of this and this. Now we've basically just done a bit flip. Now, if I were to instead have put this down here, it would be this one that has flipped, because we would apply this not on this tensor product, but actually before the tensor product has been applied. So that would actually flip this one from being a 0 to a 1, and this gives us our 1, 0. Essentially flipping that bit. That is analogous, and I've sort of written this out here, where we have two classical bits and we run them through a line and we hit a NOT gate. That's after this is what we basically are describing as this sort of it's not necessarily a measurement, but it's a determination of the state after which, or a prediction of the state. And one can say that this classically will be 1, 0. Similarly, after we've applied this X gate here, this poly X gate, we will get 1, 0. Okay. So this C0 gate is very important. I'm just going to sort of expand upon this here. So if we have a Hadamard gate and then we have a C0, which is what we describe up there. And we start out with 0, 0. That's traditional. You can input whatever you want here, but in quantum circuitry, we usually just set everything to 0 before sending it through our circuitry. Okay. So this is just a mathematical expansion of this. So we're basically saying, okay, we're gonna first apply this Hadamard, but that's gonna be only on this first element of our tensor product state, or state vector, and then we're going to do this C0 operation. And so this, I guess we could just write this as like this. So each of these components, because this is how we define C naught, this is how we define our Hadamard gate. When we apply that to our 0, 0 tensor product state, what that does, just walking through the algebra a bit, it only operates on the first state because that's what we're doing right here. Then when we sort of expand that out, we get right here, we get our vector, which then our 4 vector, which then gets applied to this 4x4 matrix. And then this compresses down to this, which may look familiar because it's our Bell state. So we have just shown how to create our Bell state using this, and further on we'll go into many more examples. One last thing I'd like to talk about before the end of the video would be how to actually determine the probability. So let's say I send a plus state through a Z gate. I want to know what can I expect to be measured, and then I measure it. What should I expect to see? And in fact, what this is telling us is the probability of it being in the 0 state afterwards, because essentially the Z state is going to constrain it to be either 0 or 1, because those are the bases for poly Z. And so, or I should say, those are the eigenvectors for poly Z. And so to measure that, what we do is we take this basis that we're measuring against here, and then we take our input value here, and we sort of multiply that across. So we just take the inner product here. And doing that and sort of expanding it, we see that the probability is actually 1/2. So we have 1/2 probability of seeing our plus state being converted into this 0 state after applying this Z gate. So the other 50% probability just goes into being 1 here instead of 0. So you basically have a 50-50 odds of seeing, I'll just write that out, % probability of observing 0 and a 50% probability of seeing this 1 state.